Hello class and welcome back to ECE205. I'm going to do kind of a two-parter here. We've got some course review material from last lecture that we didn't quite finish up. I was just going to go back over pretty much everything we did on Tuesday, a little bit of recap, and then we'll turn around and we'll do some review for the exam. There's not too much here, so feel free to move around or change, where you're at in the video and pick out the parts you need. If you're a partial fraction expert, then you should be good to go here, but it doesn't hurt to kind of review it because this is going to come up again and very testable kind of material. All right, so to start off, we're going to look at what we talked about on Tuesday, essentially, which is distinct poles and trying to turn those into partial fraction representation. So I have an example here, HS. We're going to use the residue method to find the coefficients that we stick attached to each one of these individual terms where we're breaking out the different factors that I have in the denominator. So the technique for this is just we look at the offending point, which is at s equals minus 2. You can see that if we put in minus 2 right here, we're going to have a bad time because this is going to go to 0. The whole thing's going to go blow up, and h of s is not going to be happy. So instead what we do to try to figure out what kind of coefficients to put into here to get this guy out is we multiply by s plus 2, and from there we're getting rid of that offending root, and we can assess the rest of the expression of hs at that point. So from here we can derive the two coefficients, and we just plug them in and we're all done. So we would have minus 1 over s plus 2 plus 2 over s plus 3. All right, moving on, we have repeated poles. So for repeated poles, they can be a little bit trickier, but they're actually not too bad to have to solve. We treat them just like normal residues for the highest order that they present. So if I have some form where all of these guys are distinct, but this one has some repeats, right? We call it repeat if it has a higher power than just one. Then what we do is we just say, well, I'm just going to include all the possible powers up to k, if it's a k order or k repeated root. And once I include all of those in there, I can actually treat the last one with the residue method. I'll do my other terms in terms of the residue method as well. So coming down here, you can see that at work. For the first one here of this example, I'm just looking at the root s plus 1. And to get s plus 1, I cancel out the s plus 1 that's down there, and I'm left with a residue of s plus 2 squared in the denominator assessed at s equals minus 1. This, of course, gives me 1 for that coefficient. So when I build this later on, it's going to be pretty easy. And then for the highest order, I have s plus 2 squared that I'm multiplying to hs. And in this case, you can see that if I multiply s plus 2 squared, these just cancel out all the offending root completely. And so I can plug in, I'm free to plug in, the value of s equals minus 2 because it's no longer part of that expression. Now there's some arguments to be made here for, whether or not we're dividing by 0 or something like that. But for all intents and purposes, we can assume that we can take the limit and that it's going to be relatively continuous at that point. It's going to behave nicely. All right. So when we do that, for s plus 2 squared, we end up with just s plus 1 assessed at s equals minus 2. And we end up with another coefficient here of minus 1. Now, for the middle term, which is this lower power, you could think of this as s plus 2 to the first, right? What we're going to end up doing is multiplying the entire expression by s. So drawing your attention up here at the top for a second, if we multiply hs times s, what we end up with from the original expression that I gave you is S over a bunch of stuff. Well, as I take the limit as s goes to infinity, I have a third order polynomial in the denominator and a first order polynomial in the numerator. And so this reduces down to the limit of s over s to the third. Well, as s goes to infinity, this is essentially 1 over s squared. I could cancel out one of these powers of s. This guy, as it approaches infinity, goes definitely to 0. So essentially, I'm driving this to a known value for hs. Now, why is that a good thing? Well, if I look down here again, and I say, okay, I've taken hs times s, but now instead I'm going to look at the other side of the expression and multiply all of these different terms by s. As it turns out, this one here is going to zero out for me. And this becomes important, by the way, when you have higher orders of k, because you're going to want to eliminate some of those other guys along the way. But for all intents and purposes here, I can see that for the last term, s over s squared in the limit as s goes to infinity must go to 0. So this -1 doesn't matter at all. And now I'm just left with these two terms. Well, I have a ratio here of s to s plus 2. Well, as s goes to infinity, s over s plus 2 just goes to 1. And so I have 1 times this coefficient, whatever it may be right here. Similarly, this down here, this quantity must also approach infinity, and I have infinity up in the numerator, so it's 1 times infinity overall. So I have essentially coefficients that must cancel each other out here, or I'm sorry, I have, these guys have to add up to 0. So however big they may get, these values are effectively going to approach a ratio of 1, a ratio of 1, and I have 1 plus a to the minus 2 is equal to 0. And I can just look at it in a complementary fashion and say, well, my value then for that middle coefficient must then be minus 1. Oops, there we go. 8 minus 2, 1, and we're done. We've got all 3 coefficients. We can now build the entire partial fraction. So where we got interrupted yesterday, because I was too slow, we talked a lot about the fundamental theorem of algebra. We discussed how every real polynomial, every real one, not every complex one, but every real one either has real roots or if it does have complex roots, they have to come in conjugate pairs. And what that means is that if I have some root that's of the form a plus bj, I end up with another root that is of the form a minus bj. That's just the way it has to work out. So there's proofs of these in algebra courses and things like that, or polynomials courses, number theory courses. This comes in very handy. But if you have a complex polynomial, by the way, this isn't true, and every complex polynomial can factor into monic, meaning order 1, complex roots. So you can basically fully factor a complex polynomial. You just can't do it for the reals. All right, so if I'm given some expression here, okay, some expression here that in theory breaks down into complex conjugate roots, and I know doesn't factor nicely or factor at all over the reals, then I can re-express this by completing the square and adding a constant to it. And the way that we build this, it should be a square here, the way that I build this is by saying, hey, I can just take this leading portion here, add on the bits that I need, subtract off the bits that I don't want, and keep those guys together off to the side. So it's pretty straightforward, but if you just follow this rule, you'll be in good shape. The reason we're doing any of this is Because we have two really nice Laplace transform forms. And we talked a little bit about the cosine derivation, but what we essentially have for any kind of sinusoid is it's made up of a cosine and a sine component. We can think of these as a real component and an imaginary component because the x-axis of our complex plane represents a cosine component, and the imaginary axis represents the sine component. And we can see this from Euler's identity or Euler's equation. But suffice it to say, we have to be a little bit careful about one thing in particular here, this d, because in the standard form for the sine, we end up with something that looks more like b over all this stuff in here. Right, so we just have to be a little bit careful how we approach things when we're going in for this. Now, that's not to say that we shouldn't solve for d. It just means that when we do the conversion, we might have to normalize this to get b and then something else on the outside times that b that's there. Okay. So I'm not going to do a bunch of examples of this. There's examples ad nauseum in your notes. Suffice it to say, I'm not going to give you guys crazy questions on an exam that are going to take too long, because these can get really messy in a big hurry. So just know how to do it. Know how to do the split up here where you're completing the square to get it into a nice usable form. So if you focus on kind of the early examples of this, that's something that I'm more inclined to test you guys on. The homeworks will kind of draw you through the rest of the partial fraction process. And of course, you can always just build the forms of partial fractions using the kind of common denominator methods that you might have learned elsewhere. All right. One of the biggest, again, mistakes that students tend to make that I've observed is they don't necessarily know when to use which form. So I've got the factored out form here, and then I've got the partial fractions. And when the heck do I use either one? Well, I use the factored form when I'm trying to do any kind of frequency analysis, because what this is going to give me is my pole zero plot. And the partial fraction form that we've been working on would have been today if we didn't have on Friday if we didn't have an exam, and on Tuesday and all that, that allows us to convert our transfer function back into the time domain easily, presumably easily. Sometimes factoring these polynomials can be a real pain, and then putting them into partial fractions can be a pain too. So, arguably, but I can tell you it's easier than having to solve all the different differential equations each and every single time. All right, so that concludes the lesson wrap-up stuff that I wanted to do. So now what I'm going to do is go back and do just a little bit of test review for you guys, exploring some key concepts. That way you have a really solid foundation going into tomorrow. So the two biggest ideas, or I guess the one big idea, is LTI systems, right? And the two parts of that are linear and time invariance, hence the LTI. For linear systems, they come in, they have two different important parts. Linear has to allow constants to sort of fly through the system. And if I add two different inputs, their output should be the sum as if I had put them in by themselves. So if the output for putting in x1 gives me y1 independently, then if I add that to another one before I push it through the system, the output should give me the sum of the two outputs that would have been independent. Okay. In a nutshell, just adding stuff together shouldn't really change fundamentally the way the output works. Okay. We also learned that LTI systems are characterizable by their impulse response, this very special function that allows us to define them. And that's because linear and time invariance are hallmark characteristics of convolution itself. So y of t for an LTI system is defined as the convolution of an input with the impulse response. Using convolution, we can describe linearity and time invariance. Linearity essentially boils down to I have a constant multiplied to an input. That constant is just gonna fly through at the end. I can just do my convolution and we're good to go. And the reason for that is very simple. I have a definition here for the convolution. If I have some kind of multiplication happening to A, that A can get moved out, right? I can just take this guy, bring it to the out, well, most of it anyway. I can take this guy, bring it to the outside, and now it's essentially just going to pop out for the output, okay? Now, sums are obviously going to work the same way. If we look at this guy here, we could break this out and do x1 plus x2, never mind the argument for the time being, but I have h of tau, and this can just distribute over those two terms. So it's very easy to see how convolution is going to distribute there. Similarly, for time invariance, I'm actually going to leave this outside in sort of a convolution representation. So what I end up with for this one is if I delay the input to the system, remember our Indiana Jones analogy, it shouldn't really matter when he enters, but for a lot of systems it might. But if it's an LTI system, it doesn't matter. What's effectively going to happen is we can think of the input to the system as a delta function convolved with that input, and then we can do the convolutions in any order that we like. So we can just take h of x and h of t, and then I do the convolution here to get the original output if I had sent x of t at the right time, and I just have y of t there. And then I convolve that with that delay that I had hanging on the outside, which then just gives me a delay on the output. So the long story short here is that if I'm delaying the input, it's representable as a convolution. I could wait a hot minute to take that convolution, and I can go ahead and assess the system to get yt out. And then by applying that delay outside of the context of the system, I then get the output as just being delayed. Two other important principles of systems that we discussed, a little less so than the LTI stuff, but nonetheless important, are causality and Bibo stability. Causality is very simple. The impulse response must be zero anytime we're looking at a time prior to zero. And the reason for this is a little bit complicated, but it's not too hard to grasp. If I have some kind of h of t here, and I have this, say this is 0, if I flip this around the axis, there's going to be this portion here in green that's going to be on the positive side of the axis. And you say, well, what the hell's wrong with that? That should be just fine. Except now if I think about it, let's say that I have little x of t coming along. Let's suppose that x of t started here. I don't know, let's make it some kind of exponential something or other. That's fine. That's a nice input to my system, perhaps. Okay, maybe it stops there. Now, if I redraw this green flipped over, then at time t equals 0, for my convolution, I'm going to be picking up slices or components of x that are in the future. That's no good. This is stuff that hasn't happened yet for x. Because if I look at this spot right here, I'm integrating over the entire region, the entire line here of tau, and I'm pushing green forward with time, right? But at time t equals 0, I end up taking parts of x, parts of multiplying to values of x of t that are in the future. And so causality really is representative for LTI systems of not taking any future inputs when I'm assessing the output of the system. So the current output of the system cannot be pulling from the future of x. So So at time t equals 0, I should only pull from 0 or stuff that's in the past. As I move forward in time, it should be at that wherever I'm at t and looking backwards. Bibo stability is quite simple, actually. We can just fix x at any value, and if for any value m, if it's bounded to that value over the entire lifespan, then the output must also be bounded for it to be Bibo stable. So the way I like to do these is plug in an m for x of t and see if you could get y of t to come out to be some kind of constant and not blow up. For impulse responses, what we have to do is plug in a delta function for x. When we do that, however, recognize that y of t is equal to h of t convolved with the delta function. And so essentially, for this input here, this is x of t, right? We've replaced it with delta of t. Well, delta of t with h of t is just h of t. And so in whatever differential equation or expression or however I've written my system, I can go around replacing y of t with h of t if I've plugged in the delta function for any value of x that I see running around. And then from there, you can just solve for h of t. Now, the Heaviside function and the delta function have a strong relationship. We've been talking about this delta function, how it is what we put into the system to get out the impulse response h of t. The Heaviside step function is useful for giving us the step response, and there's a duality between the Heaviside and the step function. It's defined by the derivative, right? If I look at the step function's derivative is just the impulse response. Sorry, not the impulse response, the Dirac delta function, and the step function is the integral of this little guy here. And you say, well, why is there a t and why do I have lambdas floating around here? Well, that's just a feature of the fact that I don't have an output whenever lambda here is less than 0. So if I'm looking at the delta function, right, and this is the lambda axis, this only pops at lambda equals 0. If I'm just integrating all along here, I don't actually capture anything that's non-zero until I have pushed t, that's my upper bound on my limits of integration, until I've pushed t past 0. So that's why this expression is representative of the Heaviside step function, because after I've crossed that threshold, after I've crossed 0 here somewhere, my output's by definition equal to 1. I can even rewrite this, by the way, as some arbitrarily small epsilon is equal to 1. As long as this bounds 0, I'm good to go. Okay, now for a system defined by an impulse response, what I'm essentially doing is if I can get this guy out from some other function or something else along the way, then I'm good to go. I know every single output that I'm going to get for every single input. Now, the step function and the step response are closely related. The step response is the output of the system. This is my system. When the input to that system is the step function. And so you can see that the impulse response here, I should probably do this. The impulse response, its output is h of t. Whenever my input is this delta function, the step response is when I put in a step function. Makes sense, right? It goes along with the name. Impulse response, I put in an impulse. What did I get? Step response, I put in a step. What did I get? In practice, the impulse function does not really exist in reality at all. We typically use step functions for real systems to probe them, and then we use the relationship between the impulse response and the step response to infer, given this, what this is. So the question is, what is the relationship between h of t and s of t? And if you can figure this out, you're going to do really well on the exam, let me tell you. You need to have this going into the exam tomorrow. If you don't, you're going to be very sad, okay? So if I give you an h of t, can you give me s of t? If I give you s of t, could you give me h of t? Your answer should be yes. And if it's not, you need to make sure tonight that you review how to do that. All right, everybody, that wraps up everything that I wanted to talk to you about. And I think this should give you a lot of really good preparation for the exam. It doesn't cover everything that's going to be on there, obviously. But it will give you a really, really nice head start. And if you pay attention, you actually, review the things that I told you to focus on, okay? In particular, this stuff right here, you'll be in really great shape. So make sure that you know where those are. Okay, I'll talk to you all later. See you on Monday. And absolutely hope for the best for all of you for the exam. Thank you very much.